Okay folks, today I'm going to do a video and this is going to cover three topics that are related. We're going to be looking at reflection, of a wave. That's what happens when a wave meets a boundary. We're going to be looking at wave interference, and superposition. This is what happens when a wave meets another wave. And then we're going to look at how these two things can happen at the same time and sometimes produce something called a standing wave or resonance. So those are today's three topics: reflection, interference, and standing waves. How do you get standing waves? Well, you've got to learn about reflection and interference first. So let's look. We have a string here going through a window, and I can send wave pulses through this string. They go at a constant speed and they have a certain amplitude. The amplitude right now, down at the bottom left, is 0.5 centimeters, and we can measure that to confirm it. The amplitude is the distance from the equilibrium, so at the highest point there, it does look to be about 0.5 centimeters. So that's the amplitude of this wave pulse. From here to here, it is 0.5 centimeters. That's the displacement of that particle, and it's the maximum displacement, so that's called the amplitude. And this is the thing we're going to be paying attention to for this entire video, is the amplitude of these waves and wave pulses. Okay, so first of all, let's talk about reflection. Reflection, remember, is what happens when a wave meets a boundary. What is a boundary? There's two types of boundaries. I will restart this and I will show you. Take my ruler away. Now, right now I have no boundary. It just goes straight out the window. But I can choose two types of boundaries. I can choose a fixed end, and here the simulation shows this last particle is fixed. It's clamped in place. It can't move up or down. It's prohibited from moving up or down by this clamp. So this is called a fixed end. Now, just so you know, this will also be a fixed end. This particle is connected to the motor or the pulse generating machine, and it's actually fixed as well. Now, what happens when I send a wave pulse through this string and the wave pulse meets this fixed end? Let's observe. So we should be noticing two things here. One thing is that the amplitude changes from positive to negative. Okay, that is what happens when it meets that fixed end. The other more obvious thing is that the wave is reflected. It bounces off of the fixed end and goes back in the other direction, and then again. This is called reflection. Okay, what's changing is the polarity. Here the amplitude is positive. We have a positive amplitude, and then when it hits the boundary, it's going to flip to a negative polarity or a negative amplitude. Okay, the polarity changes when you have a fixed end. Right? Let's see what happens when we have a loose end. The same thing is not going to happen. Okay, so now we don't have a fixed end. This end down here is still fixed, but on the right hand side, now we have a loose end, or what I call, and most people will call in your textbooks, a free end. Here, the particle, that last particle, is allowed to move up or down. The pole does prevent it from moving side to side, but now it can move up or down. That last particle is free to move, so we call it a free end. Now let's send some wave pulses and observe what happens. Okay, so only one thing changed. We still get that reflection. The direction did change. That's called reflection. But the other thing that did not change is the polarity of the amplitude. When it hits that free end, whether it's negative or positive, it's going to reflect back and still be negative or positive. Whereas the fixed end, the polarity always changes from negative to positive or positive to negative. Okay, this is called the incoming wave. This is called the incident wave. And when it's reflected, we call it the reflected wave. And when you meet a fixed boundary, the polarity of the incident wave will switch when it goes to the reflected wave. And when the incident wave hits a free end, the polarity of the reflected wave will be the same. Okay, so there's two takeaways from this, two main ideas. For a fixed boundary, the amplitude, the polarity of the amplitude will change. For the free end, or the free boundary, the polarity doesn't change. And there's one more thing you may be wondering about. What about the amplitude? Does the amount of the amplitude change? Well, it doesn't. Let's clean this up a little bit and we'll take some measurements to prove that. Okay, now whether I have a free end or a fixed end, while the polarity may or may not change, the amplitude, how far it is from the equilibrium, will not change. So right now it's at 0.5 centimeters. That's the amplitude of this wave, this particular wave, about half a centimeter. And when I let that go, and it reflects off the fixed end, it's still going to be about half a centimeter. The amount didn't change, only the polarity. The same thing happens with the free end. It goes in at half a centimeter. When it reflects off, it's still going to be at a half of a centimeter. Okay? So only the polarity changes from positive to negative when you get a reflection. Okay? And the only time polarity changes is with a fixed boundary, not a free boundary. Okay, now we're going to move on to the next topic, which is going to result from reflection. It's called interference. Interference is what happens when a wave meets another wave. Okay, and there's two types of interference. There is constructive interference and destructive interference. Okay, and we're also going to talk about superposition, which is related to interference as well. Okay, so those are the next two topics. Interference, when a wave meets a wave. So let's let that go. So here's one wave. It's going to go to that free end and reflect off. I'm going to send another wave behind it and put it in slow motion. Now, the amplitude of each of these waves is half a centimeter. But what happens, this wave is now moving to the left. This wave's moving to the left. And this wave's moving to the right. What's going to happen when they meet, when they try to occupy the same space on the string? We're going to go in slow motion, step by step, to observe. They're starting to overlap. And now here you're going to see the amplitude is now gone above 0.5 centimeters until they completely overlap, and about right there they've completely overlapped. Now we have, this is called a superposition. The superposition of these two waves, let's measure it, is 1 centimeter, twice as much as the amplitudes of the individual waves. The superposition is actually a mathematical thing. So the superposition is actually the amplitude of the combined waves. So the amplitude of the combined waves will be equal to the amplitude of wave 1 plus the amplitude of wave 2. In this particular case, both A1 and A2 had an amplitude of 0.5 centimeters, and they were both positive because they were above the equilibrium. Okay, so the combined amplitude, or the superposition of these two waves, is 1 centimeter. And that's superposition. Now, how did we get this superposition? The way we got the superposition is that the two waves interfered. How did they interfere? They interfered constructively. This is what happens when the waves have the same polarity. You can see that the superposition is greater than the amplitude of the individual waves. So this is called constructive interference, and that happens when the wave pulses have the same polarity. Let's look at the alternate case. Now I'm going to send a wave down this string and let it reflect back, and there we go. Now I have two waves going towards one another. One is moving to the right and the other is moving to the left. Now the amplitude of this wave is negative 0.5 centimeters, half a centimeter. And we can measure that to make sure it's right. It's about half a centimeter. Now this is negative because its polarity is negative. It's below the equilibrium. This wave has the same magnitude of amplitude, but it's got the opposite polarity. It's above the equilibrium. So we're going to say A2, the amplitude of wave 2, is positive 0.5 centimeters. Now the superposition, the combined amplitude, when they overlap, when they interfere, should be A1 plus A2. And that should come out to be 0. That should be the combined amplitude when these two waves interfere. Let's see what happens. We'll do it in step by step. Okay, they're starting to overlap. They haven't completely overlapped yet, and then there. They've completely, more or less, overlapped. And you can see that you can't even see a wave. There is no amplitude. The amplitude is 0. So here we have a combined amplitude, a superposition of 0. Okay, this is called destructive interference. This is what happens when the wave pulses have opposite polarity. When one wave has a positive amplitude while the other has a negative amplitude, you're going to get destructive interference. And with destructive interference, the superposition is less than the amplitude of the greatest of the two wave pulses. Okay, so in constructive interference, they have the same polarity and the amplitude is greater than the individual amplitudes. And with destructive, they have the opposite polarity and the superposition, or the combined amplitude, is less than the individual amplitudes. So let's get all that written down. Superposition, that is really just a combined amplitude when two waves interfere, and that's just the amplitude of wave 1 plus the amplitude of wave 2. You have constructive interference when A combined is less than A1 and A2, and you have a destructive interference when the combined amplitude is less. I messed that up. You have constructive interference when they have the same polarity and the superposition amplitude, or the combined amplitude, is greater than A1 or A2. And when you have destructive interference, they have the opposite polarity and the combined amplitude should be less than A1 or A2. All right. Now, with all these phenomena together, interference, superposition, and reflection, we can produce something called standing waves, and that's the next topic we're going to. Standing waves. To understand how to produce a standing wave, you first have to understand reflection, what happens when a wave meets a boundary, and interference, what happens when a wave meets another wave. With these two things, we can produce standing waves. Okay, so I'm going to set my source, I'm not going to do pulses anymore, I'm going to set it to oscillate so that my frequency source is periodic, making a periodic wave. Okay, so he's sending out periodic waves. Okay, and you can see they get reflected and then pass through the additional waves that are being sending out. So in standing waves, here's what we have going on. I'll restart it. The frequency source sending out waves, reflecting off of a boundary, but when they reflect, they're going to interfere with the waves following behind them that haven't struck the boundary yet. And this process continues. They will then reflect off of this boundary and go back and combine and interfere with the waves reflecting off of this boundary. And we get this continuous bouncing back and forth and this continuous interference. Okay? Now, when the frequency of the source is just right, I can get something called a standing wave. Right now, the frequency isn't just right. The amplitude doesn't really matter, but I am going to turn it down for the purposes of this demonstration to about 10 centimeters. Restart, pause. Okay, so let me set this frequency to a special frequency that I calculated, 0.43, I believe, 0.42. Now this frequency is special for this length of string under high tension. Watch what happens. Why not? The amplitude's really tiny. It's only 0.1. And then it's going to reflect off of the boundary, and of course that will invert. But when this is reflected, this is sending another one out. And now it's happening at just the right time to where the wave that's sent out and the wave that's reflected will always interfere constructively, and the amplitude continuously increases. Since I have no energy loss, dampening's all the way down, this is continuously constructively interfering, increasing the amplitude, and giving energy to my system. This is called a standing wave. The reason it's called a standing wave is because it looks like it's standing still. It doesn't look like it's moving right or left. It just looks like it's oscillating or vibrating in place. Okay? Now, this isn't the only special frequency. This is just called the fundamental frequency. This is the first frequency that produces a standing wave. It's also called the first harmonic. It has these parts. It has two nodes. There's a node right here, a place where displacement or amplitude is at a minimum. So that means we also have a node here. Usually the displacement is 0 at a node, the amplitude is 0 at a node. And then we have regions of maximum displacement. Let me pause this. This region, this part right here of maximum displacement, this is called an antinode. And you can see that we have one antinode for the first harmonic. Let's look at some other harmonics. There's an infinite number of them, and we're going to look at 3. So let me I'm actually going to change my frequency first. I'm going to take this, I'm actually going to double it. I'm going to change it to 0.83. All these values are rounded, by the way. So 0.83 is another special frequency. Let's see what happens. You can see that amplitude is increasing, and we get another standing wave. But this wave has a different number of nodes and antinodes. See if I can get the timing just right. And there we go. This has 3 nodes. There's a node here. There's a node here. A node is where displacement is 0. And then you have another node right here. 3 nodes. And then how many antinodes do we have? We have 2 antinodes. We have an antinode right here. That's where the displacement is at a maximum. So this is also where you would measure the amplitude of the standing wave. And then we have another antinode right here. And you can say we have 2 antinodes. That is because this frequency is F2. This is called the second harmonic. And the standing wave has 2 antinodes for the second harmonic. Let's look at one more. I'm going to change this to 1.25 now. 3 times as much as my original frequency. Restart it, and let's watch what happens. You're going to see a node form here, and you're going to see a node form here. And then you're going to have 1, 2, 3 antinodes. And there we go. I paused it so you can see them clearly. We have 3 antinodes, and how many nodes? Not 2, we have 4. Because remember, these are also nodes. And we have 1, 2, 3 antinodes. This is the third frequency, the third highest frequency that will give us a standing wave. This is called the third harmonic frequency. Okay, so that is standing waves. Standing waves are what we get when we have reflection, interference in just the right conditions. In other words, when this is happening at just the right frequency, we can get standing waves. Alright, I hope this video has been helpful. Thanks for watching.